Thank you very much. My esteemed colleagues have already done all the hard theoretical work of setting up physical intelligence. And my rather simple task is to tell you about the concrete stuff, the system that we actually use to test out some of these theoretical ideas. First, I'm going to describe the anatomy of what we call e-SOAP, or electronic SOAP. We have versions that are actually in other media, but for today we'll talk only about the electronic version. I'll show you that e-SOAP, as is required of discrete structures, shows us rather remarkable criticality and really extreme hysteresis. I'll show you an example of e-SOAP giving us a little bit of proto-foraging that is actually searching for I won't call it, but searching for the energy that maintains it and also that creates it. And finally, we'll take some initial moves towards how we might get e-SOAP to do more than just search for that one energy source, but actually try to detect other energy sources in the environment. So first, a little bit of anatomy. One of the nice things about e-SOAP is that so far, I hope actually into the future, it all happens in a single petri dish. Okay? It doesn't get up and move around very much. There is a source electrode that is spraying high voltage electricity, which isn't really quite as scary as it sounds, over the dish and onto the surface of some oil. We've been using Mazola, but Wesson also will work with it as well. Inside the oil, there is a collection of what I'm going to call beads. You'll see that in a moment they're going to turn into slightly different things, but generally think about these as ball bearings. There is a grounding electrode on the interior of the dish. It doesn't actually have a gap as in the picture. I just left that in there so you can continue to see the bead. It completely encases the oil. So here we have the side view that we just developed. And here we have another view that we're going to see on and off, a top view. Okay, so here, of course, is the source electrode, the grounding electrode, and these are our beads doing some little minimal SOAP activity. All right, what I'm going to show you next is a movie where we actually have a bottom view, much like the top view, but we're shooting up through a plexiglass table, and what you'll see is the beads are all initially contained in a little kind of circular pattern in the middle. They're actually held there by gravity. You won't be able to see the gravity gradient, but it's within a little watch glass. Okay? And as we apply voltage, you'll see the oil starts to move. Charge begins to build up on the beads themselves. And they will begin to move. In this situation, and in most situations, we increase the voltage stepwise. So literally, simply we ramp it up, we let it go for a little while, we ramp it up, we let it go for a little while, and that'll become relevant in a moment. The meter on the power supply says about 30,000 volts. It turns out to be about 20,000 volts. Which is a little bit of a surprise to us, but it was good to our instrument. So here we see some initial motion. While all this is happening, thanks to the amazing technical abilities of Dr. Bruce Kay, we are able to sample the system at 2,000 hertz. We are taking the voltage, the current going through the system, and the temperature. That moment that just passed there is what we call the grounding event. Okay? And now it's sort of a mature, fully formed structure. The main quantity that we talk about is entropy, the rate of entropy production, which is simply the voltage times the current divided by the temperature. So as I said, SOAP exhibits criticality and hysteresis. First, let me give you a boring baseline story, which just sort of sets the stage for understanding what's happening. So here we have a situation in which we remove the beads from the oil. We just have a dish of oil, and we're spraying charge on it. And we're increasing the charge in the stepwise manner. And we're just basically cooking this oil with very, very low voltage. Okay? And what you can see is, as you might expect, nothing particularly interesting happens. As you ramp up the voltage, the amount of entropy production increases. And as you step the voltage back down, it decreases again. So that's not particularly interesting. But it does serve as a nice comparison to when we have both the beads and the oil together. So here we have the same situation, but now the oil and the beads are both present. Let me draw your attention to this little region here. And this is a critical grounding event. So there is a constant voltage being applied, but right here we have the formation of the tree structure. And suddenly, you'll notice that now we go from having the entropy production for oil being greater than that for beads and oil to the reverse situation. So we have a very clear signature that this formed structure is actually doing something considerably different than the system was doing before it formed that structure. And interestingly, it maintains that difference even when we step the system down below what was the critical threshold. Okay? So a nice demonstration of hysteresis. So we see here that indeed the green, oils and beads, is above the red, and even here, which is the lowest amount of voltage that we can apply to the system. So it shows us extreme hysteresis. That structure, you can still see it, but it's also still doing something functionally. Sophie also shows us what we call proto-foraging. That is, it searches in the oil for what we might think about as strong pockets of electrons. That is, places where the field is particularly dense. You can see that happening here. The PowerPoint's making it a little more jerky than it really is. It's actually quite smooth and beautiful. And so she's moving around very nicely there. Before we had this instrumented, we thought that indeed this probably was what was happening, that we were seeing Sophie move to actually pick up richer regions, move to richer regions to pick up electrons. Once we had an instrument, we could actually see that was what was happening. So entropy production increases during periods of motion and decreases when the system just stays still in the station. So the system is showing us this evidence of rudimentary foraging. Finally, let me tell you a little bit about the development of proto-sensors. So while foraging, as we see it here, is certainly something that we want, we actually want a little bit more than this. When you think about what an organism does, it's not just that you're moved by the presence of the energy source that your system uses to maintain itself. Right? It's not like you're drawn to food by the properties of it being food. We actually want Sophie to be able to detect information in the environment through other energy fields, other than the one that creates and maintains. This is an important thing for it to be able to do. But at the same time, it's a very simple system. Right? It's beads and it's oil. And that's all it is. So we don't seem to have, initially at least, enough homogeneity in the material to make that happen. So in order to get some sort of initial move toward the sensor, I want to propose that we need something along these lines. We have some minimal requirements that seem necessary in order to actually make the system do proto-sensing. We need some of the elements to be sensitive to a second type of energy. So we might say that the yellow ones here are sensor elements, and that the blue ones are non-sensor elements. But we need all those elements to become part of the dissipative structure on their own. Right? There's nothing special about them. And in fact, if you were to just look at the structure as it forms, you wouldn't even know which ones were the sensor elements and which ones were the non-sensor elements. So all the elements are sensitive to the original field, but some of them have this additional property of being sensitive to some sort of secondary field. The imposition of the second field is going to directly affect only the sensor elements, right? Because the non-sensor elements don't have the proper physics to be sensitive to that secondary field. But because they're all part of the same dissipative structure, when you perturb the sensor elements, it turns out you're actually going to be perturbing the entire structure simultaneously. So let me use this figure to build a little bit of an example, which I'll then show you in the real world. And so our secondary field here is going to be magnetism. So our sensor elements are going to be ferrous material, sensitive to magnetism. Our non-sensor elements are going to be non-ferrous material. So when we apply the magnetism, they're not going to care about those. We're going to have a source electrode, which as you see is a little bit off-center here for reasons I'll use in a moment. And we're going to have an occluder. So the occluder sits between the source electrode and the surface of the oil, and what it creates essentially is a shadow, a low energy region. Right? Sophie does not like low energy regions. Too much low energy will kill Sophie off entirely. Okay? So a low energy region is suboptimal. You should also note that beyond the shadow here is a rich energy region. Right? If this were a light, right, this would be bright here, this would be bright. So the task for Sophie, and admittedly it's a very simple task, is to move out of the low energy region into the high energy region where things are better. The question is, if we apply a magnetic field, by placing a magnet in here, can we make this happen? And can we make the structure go and move into this high energy region? A very simple first step towards making the system respond to a second field in the service of getting to a richer region as the original energy source, the energy source that it needs to maintain. All right, so just to orient you, here is our source electrode. Here is our very high-tech occluder, piece of plastic. Here is an already formed Sophie that is set up, right? So this is already formed under usual conditions. And some of these elements are ferrous material, some are non-ferrous material. Okay? And what's going to happen is I'm going to turn Sophie on, and you'll see it's going to reground, and then the magnetism. Okay, there's the grounding event. You can see in here, it's not very stable. And here comes the magnet. Right? And it organizes to the magnet. The ferrous materials go to the magnet, of course. Right? But the whole structure is actually reorganized and becomes more stable because it's moved itself into a region that has high energy and that's stabilized. So first, this is a very small step towards including a second field that provides some information about where it's better to be. So, just to summarize, we have shown that Sophie exhibits criticality and hysteresis, which is a necessary property of the dissipative structure. We've shown that it does a little bit of proto-foraging, that is, it's able to move in service of obtaining the sorts of energy that it needs to maintain itself. And we've made some initial steps towards creating a proto-census, that is, creating a SOFI that has enough heterogeneity so that it is capable of detecting secondary fields in the environment that it can use in service of maintaining its own. Thank you very much for your time today.